came from Temple University, where he worked on an experiment at Brookhaven National Laboratory studying conservation laws using rare decays of K0 meson. And then came to Rutgers for a postdoc, where we were working on experiments at Fermi Lab, studying CPT violation or searching for CPT symmetry violation. We got within about a factor of 10 on the Planck scale of that experiment. And then looking for direct CT violation. And then John got interested in cosmic rays and was at Montana State and then Montana as an assistant professor. And during the high-res experiment, collaborating with the cosmic ray group here. And then John came here in 2005 to concentrate on research in cosmic rays. And here he is now.
Thanks, Gordon. And, you know, I've wanted to point out that, you know, Gordon mentioned that I came to Rutgers as a postdoc. Recently, Gordon and I passed our 20-year anniversary of working together. Gordon would probably say that I'm responsible for a lot of the gray hairs on his head.
Everything that went wrong in all those experiments
was mostly due to me. But yeah, so Gordon and I have been working together for a long time, and thanks for that introduction. So I'm going to talk about the topic of current and future directions of ultra-high energy cosmic ray research in Utah. This is a big topic. This is an ambitious topic because we have a lot of things going on here. So I'm trying to, you know, kind of selectively identify what are the big issues, the current, you know, status in the most important questions, the energy spectrum, the chemical composition, and the search for arrival direction anisotropy. And I also want to then talk about what we're doing right now to prepare for the future, sort of the next 10 years and beyond of cosmic ray research. If I have time, I have a couple slides I want to present on novel uses of cosmic ray detectors, radiation detectors out in the desert that I'd like to talk about. Okay, so this is my introductory slide for the cosmic ray energy spectrum. This is an area of research that was for 4 decades or more driven by the question, can we see the predicted end of the cosmic ray energy spectrum that was predicted to arise as a result of particles interacting with the cosmic microwave background? Okay, so shortly after the cosmic microwave background was discovered in the mid-60s, 3 people pointed out that this is going to place a energy limit and a distance horizon limit on the highest energy cosmic rays. And the end of the spectrum was indeed observed in Utah in a paper published in 2008. I actually gave a colloquium on this topic back in 2007. Some of you may remember. But this plot here is the punchline of that paper. This is a plot of the energy spectrum as what typically what we do, multiply the flux, the vertical axis, by energy cubed to take out the overall energy cubed power law dependence so that we can see structure in the spectrum. And the interesting feature is this one here, okay, where above about 10 to the 19.6 electron volts, the spectrum abruptly cuts off. If you ask what's the statistical significance of continuing this power law beyond that point, it's about a 5 sigma deficit. What would be there if there were no end to the cosmic ray energy spectrum? Okay, so this is a important observation. Really a kind of climax within the past decade in the field of cosmic ray research. Okay, so that was 5 years ago. Now the situation, different experiments are starting to measure the same, or measuring the same thing, and at the level of 10-20%, the results are all consistent. Okay, so this is a superposition of the high-res results, results from the Pierre Auger Observatory, which have the same general shape, although there's a systematic difference at about the 20% level. But the shape is the same. Disagreement is within systematic uncertainties. And also the telescope array surface detector spectrum is the black points. So this is from this figure is taken from an APJ about the telescope array surface detector spectrum. All experiments nowadays see a cutoff. There's clearly a change in the index. This feature is called the ankle, around 10 to the 19.5 electron volts. And something that Doug Bergman pointed out in his colloquium last week is that fluorescence is important. Okay? Having the ability to do calorimetric energy measurement of these air showers, as opposed to just seeing the footprint as you do with a surface detector, really made the difference in getting all these experimental results to converge. Before this, there were experiments that seemed to see continuations of the spectra beyond the GZK cutoff. Really, it was bringing fluorescence into the picture, an innovation that was pioneered by people at Utah that enabled us to get this, what I consider really good agreement in the energy spectrum. Okay, so after that, what questions remain? Can we explain all the spectral features? Is this cutoff really a GZK effect? Or is it coincidentally a cutoff in the source production spectra that just happens to be at the right energy? Okay? How might we resolve that? Well, if we can identify sources, that might tell us something about what's really going on here. There might be hints from the chemical composition, right? Couple models for what's going on here. What I call the GZK prime effect, in which protons interacting with the microwave background undergo E plus E minus pair production, could excavate this angle feature, or it could be a change in sources. We could be looking at a transition between galactic cosmic rays, which are going to, we expect, be fairly high in mass in A, to a mostly protonic extragalactic component. So composition can maybe tell us something about that. Also, there's a feature here that's been observed by a number of experiments called the second knee in the jargon. Is that kink real, and what is it? Again, is there a composition change? Is there a source change that goes along with it? So these are kind of the important questions that we want to address through composition and anisotropy studies. Okay, so this is a picture I'm sure everyone here has seen of the Telescope Array Observatory, located about 2.5 hours south of here, outside of the town of Delta, Utah. It consists of a surface detector array, surface scintillator detectors covering about 700 square kilometers, which Doug pointed out, nicely fills the Salt Lake Valley. This measures only the footprint of the air showers, so it's not capable of the calorimetric energy measurements that we're capable of with fluorescence detectors. Okay, but it does have one big advantage over fluorescence detectors, which has a 100% duty cycle. We collect data 24/7, 365. Fluorescence detectors, we have 3 of them in telescope array at Middle Drum, Long Ridge, and at Black Rock Mesa. These are designed to overlook the surface detector array, so each event that we reconstruct, we're reconstructing in principle in hybrid, using both technologies. We reconstruct the full longitudinal development of the shower. Disadvantage is 10% duty cycle. Okay, this is a picture of one of the fluorescence detectors. Large light bucket mirrors are collecting information from the night sky. projecting it onto a photomultiplier tube camera. Each pixel in this camera is about a degree of the sky. And then this is a reconstruction of an air shower that passed through the field of view of one of these cameras. Okay, what do we see? Okay, the positions in the sky of pointing directions of each mirror, of each phototube pixel. The energy deposited and time is the axis in color, showing the development of this shower. So the shower profile is the next step in the reconstruction. Okay, so this is a plot of the number of charged particles as a function of depth in the atmosphere in these weird units of grams per centimeter squared. And it's from this profile that we extract the energy of the air shower. Okay, basically the energy is going to be proportional to the number of charged particles, which is going to be proportional to the fluorescence light produced. Okay, so it's the height of this plot that tells us about the energy. The composition, on the other hand, comes from the depth of what is known as air shower maximum, okay, where the charged particle distribution reaches its peak. Lighter particles are going to tend to penetrate deeper into the atmosphere. Heavier particles are going to not penetrate as deep, are going to interact sooner in the atmosphere and tend to have a lower value for the air shower maximum. This is the results of the highest statistics shower maximum measurement from the high resolution fly's eye. I gave a colloquium on this topic in 2009, I think this one was. And this is a plot from a PRL. This is a result of analysis done by myself and Bill Hanlon. Well, basically, we have the expectation that the mean value of X max should go as the log of the energy for a particular species of primary cosmic ray, and will evolve in a linear way with energy as well. What the high-res results seem to show is that within the uncertainty of different high-energy hadronic interaction models, that the composition was mostly light. There are uncertainties in these hadronic interaction models, I'll say a little bit more later, basically arising from the fact that we have to extrapolate from energies at which we can do direct measurements, for example, at the LHC, to the energies 10 to the 18th, 10 to the 19th electron volts. Okay, but I'll return to this in a little bit. We have some hope to improve on that situation. If we take the high-res points, plot them, do some acceptance correction, and plot them on the same elongation rate plot as the data collected from the high-res prototype experiment, that's the red points here, you see that it looks like there's evidence of a shift from a mostly light composition to a composition that gets heavier as I go down in energy, starting at around 10 to the 18.5 or so. Now, unfortunately, most of the points with the steep elongation rate come from one experiment. Most of the points with the shallower elongation rate come from another experiment. Obviously, it'd be nice if one experiment could span this entire range of energies. Okay, and that's the motivation for an experiment, or one of the motivations for an experiment I'll be talking about in a minute, the TA low energy extension or TAIL project. I made the comment that composition could say something about this angle feature, whether that was actually a transition between galactic and extragalactic cosmic rays, or whether that was something that was coming from the GZK prime effect, the E plus E minus pair production effect. And the high-res data by itself you can see rules out models in which the angle is the location of a transition between heavy galactic and light extragalactic cosmic rays. Okay, so this is the elongation rate we would see if there was a smooth transition between iron and protons at the location of the angle, and the high-res data appears to rule that out. Okay, so that was a few years ago. What is the current situation in 2013? Our telescope array is starting to make composition measurements. This is an elongation rate measurement that was done by Monica Allen, a Utah student, and her results, this was a hybrid result using one of the fluorescence detectors and the TA telescope array surface detector. This result appears to give something consistent with a protonic distribution between 10 to the 18th and 10 to the 19.5 electron volts. A telescope array has a smaller stereo aperture than high-res, so we're still collecting statistics. Results are light, but with large statistical uncertainties. It would be nice to reduce the size of those uncertainties. On the other hand, in the southern hemisphere, there's a experiment known as the Pierre Auger Observatory. And what they appear to see is something very different, okay? Whereas things are mostly light, around 10 to the 18th electron volts, as you go up in energy to a few times 10 to the 19th, they see a definite increase in the mean in the mass, a decrease in the mean X max, which corresponds to an increase in the mass. So there's a north-south issue at play here. More statistics will help, but I think what really we need to do is understand differences in methodologies between the two experiments. Okay, what do I mean by that exactly? Let me show the elongation rate plots. Take away any model-dependent predictions, but just the actual mean values of X max as a function of energy that are reported by the two experiments. And what one sees is, although they agree within systematic errors at the highest energies, the Auger mean X max points are actually deeper than those of high-res. Okay, remember I said deeper means lighter. Okay, so there could be detector-dependent effects here, but how do the Auger experimenters interpret this as being something that's getting heavier when, at least to first order, their mean X max is no deeper than ours and perhaps a little deeper. You know, we're on the edge systematically speaking. So aside from detector effects, is there a difference in how the data is being interpreted via the Monte Carlo simulations? One of the things that myself and others are doing now is to actually start to talk to our competitors in the South, imagine that. And what we are doing is, so far at two conferences, the most recent Cosmic Ray Conference this year, a conference, UHECR 2012 in CERN a year and a half ago, starting to publish, starting to work together before these conferences to answer specific questions about each other's methodology and to do cross-checks on one another. Okay, so hopefully, in addition to obtaining more statistics, this collaboration between two groups that have apparently discrepant results will lead us somewhere good. Okay, anisotropy. So this is my transition slide to anisotropy, which is the state or quality of having properties that differ according to the direction of measurement. I want to add another definition to this slide, and this is something that Isaac Myers, my graduate student, taught me. Good graduate students teach us things too, after all. And that's the definition of the word apophenia. Apophenia means the human tendency to seek patterns in random information. And these two words are linked pretty strongly in my mind when I think about anisotropy studies. So what is the status of anisotropy studies? If you look above 57 times 10 to the 18th electron volts, we're starting to get to the regime where we can trust the pointing directions of charged particles that are coming to us from outside of our galaxy. Okay? These are the energies at which the deflections by extragalactic magnetic fields are going to start to become small relative to the uncertainties in the pointing directions that come from the resolution of the detectors. Okay? So we look at the highest energy events and superimpose them on a map of the sky. Now, telescope array is a northern hemisphere detector, so that's why the northern part of this plot is populated and the southern part is not. Okay, but put your apophenia to work and ask, are there any patterns in this random data? If one were to construct a significance map for what we see using a 25-degree spot size, that's a spot size that's suggested by angular autocorrelation studies. What one sees is that there is indeed a hot spot just south of the supergalactic plane where it looks like there's a excess. On this plot, that's about 4 sigma. How do we understand the real significance of this? Go ahead.
So is that sigma just at that spot, or is
That's
that sigma
that's
discounted for looking over there?
that's at that spot. Okay, and then the next bullet is the number that you want. Okay, so we generate a large number of isotropic data sets and ask what fraction of those isotropic data sets see a point that's at least as significant as this, and the answer is about 1.2%. So this excess is somewhere between 2 and 3 sigma in significance. Okay, so then in case your apophenia didn't detect that, I've circled that hot spot with this circle here. What is the explanation of this? Is the distribution of events following the distribution of large-scale structure? And this is a result of a telescope array APJ publication in 2013. Here in this sky map plot, and I think this is in galactic coordinates now, the shades of gray represent the distribution of matter out to a distance 250 megaparsecs, is it? Out to a distance of 250 megaparsecs. In other words, the GZK distance horizon, and the dots represent the points. You do a study of the chance probability under 2 different scenarios. One that the observed correlation is arising randomly from an isotropic distribution. The other from the model in which the arrival direction tracks the large scale structures. You see that the chance probability from an isotropic distribution is fairly small, less than 1%, whereas the chance probability from a distribution that follows the large scale structure is reasonable, of order 10%. Okay, so one possible explanation for the hotspot. Okay, so that's the kind of current situation with regard to with anisotropy composition. Okay, we've made some arguments that, yeah?
Sorry, on that last slide, why is the value of your isotropic distribution not the same as the value you showed 2 or 3 slides earlier? That was 1.2%?
Well, we're asking a different question.
I thought the isotropic
Now, we're asking a different question. Here we're asking the question, is this clumpiness that your eye sees significant compared to, if you looked at a large number of isotropic data sets and said, is there anywhere in the sky in any of these isotropic data sets where you would see an excess this big? Okay, here we're asking a specific question. We have a model that says that these particles should be tracking the dark spots on this plot. Okay, the dark spots within the GZK horizon.
For the green curve, that's true. Right, but the blue curve, isn't it?
Right, and it's saying what is the probability that a isotropic data set would give you correlation with the large scale structure at the same level that the data points to. Okay? So asking slightly different questions about the data compared to the isotropic data set. Okay, so I'm about at the halfway point of my talk, which I guess is a good place to be to switch to the discussion of the future. What upgrades do we have lined up for telescope array? And this map of telescope array, hopefully 3-4 years in the future, kind of summarizes all of that. Here is our core surface detector array, the red dots. Currently under construction is the telescope array low energy extension, or TAIL. And the motivation for this is, I pointed out this kink at a few times 10 to the 17th, asking the question, is that a real effect? Is that accompanied by any change in composition that we can observe? Does it have anything to do with this rollover here? So the astrophysics motivations we mentioned before. The end of the first knee, studying the second knee, seeing if we can see evidence for galactic to extragalactic transition. Another prospect that I find particularly exciting is we're getting with TAIL down to energies where we can do cross-section measurements at center of mass energies comparable to what is done at the LHC. I'll say something about that in just a minute. So these hadronic interaction models, right, which rely on extrapolations from LHC energies up to where we are, we're now getting down to the regime where we can do direct measurements, direct comparisons, and understand the differences. Okay, so this is just a picture. The TAIL surface detectors are being deployed. The way you go to lower energy with surface detectors is you bunch them closer together. The fluorescence detector was at the middle drum fluorescence site was modified to include another couple of rows now looking up to 60 degrees in elevation angle. That's because to go lower in energy in fluorescence, you look higher up in the sky, closer to you. Combining the two of these, this is a plot which predicts the number of hybrid events we're going to see in the TAIL observatory within 1 year. Okay? And you see it spans from 16 or 10 to the 16 to 10 to the 18.5. And right near the middle of that is the energies, the center of mass energies that are accessible in proton-proton colliders at the LHC. Okay, so what do we want to do? With TAIL, we can do proton-air total cross-section measurements, okay, at the same energies, at the same center mass energies that are accessible by the LHC. The way one does that, one looks at the X-max distribution at a particular energy, and then you fit this falling tail to an exponential, okay, and that that exponential is going to depend on the proton air cross section. Okay, so this is a plot actually from an Auger publication. Okay, here's a measurement that was made at few times 10 to the 18th. High-res also has a measurement, Belz et al. Is this point, okay? And we're talking about now pushing down into this region. Now, there are other measurements that have been done, or other attempts to do this measurement, but you look at the times of these were all something like 20 years ago, okay? Our understanding of detectors, our ability to model the interaction, hadronic interaction models, to understand the interplay between air shower geometry and detector acceptance has improved a lot, and we think we can do a much better job and reduce these error bars at energies that are meaningful for comparison with what's going on at the LHC. Okay, so this is a measurement that I'm particularly excited to see from tail. Okay, the other upgrades we want to do, we want to increase our aperture for detecting cosmic rays at the highest energies, 50 EeV and above, so we can press these composition studies, or excuse me, press these anisotropy studies. Hopefully see these features in more detail. And what we're hoping to do is increase the total size of the TA surface detector array by a factor of about 4. Okay. This is going to include adding about 500 SDs. That's the same number that we currently use in the core SD array, but these are going to be spaced 2 kilometers apart. Okay. And that's going to increase the aperture at the highest energies. And we're submitting proposals for that this fall in terms of what we're going to be able to do anisotropy-wise. By 2019, 6 years from now, we're going to accumulate 20 TA-SD years worth of data.
So you don't need fluorescence detectors, you don't need to make hybrid measurements for that anisotropy?
Well, we are adding an additional fluorescence detector. Okay, it's probably going to be located here, looking that way. What the fluorescence detector does is enable us to calibrate well the energy scale of the surface detectors. Okay, by looking at events that you observe in both. But because fluorescence only operates 10% of the time, there's a big that's a big crutch in terms of getting statistics, which is what you need for anisotropy studies. Okay, so we have enough fluorescence detectors that we can calibrate the energy scales of our surface arrays, okay, but a big enough surface array that we can really make this into a anisotropy engine, something that's going to get statistics to do the anisotropy studies that are the main motivation for this. Go ahead.
That calibration, each detector has its own sensitivity as a function of energy, or is that, are you just, every single one the same, just applying some calibration overall to shift this?
I guess the simple answer is it's more of an overall. It's more overall. After reconstructing, an air shower hits a surface detector, it's going to light up a number of the detectors depending on the size. Okay, you're going to. I don't have any slides about how surface detector energy calibration works, but basically by looking at the lateral distribution of particles, you can make a model-dependent guess as to what the energy should be. Because there are limited, because the models don't quite work. Okay, that guess gets you maybe within 20-30% of the right answer. Okay, and then by doing comparisons with the fluorescence detector energy scale, you tweak the surface detector energy scale.
But if your surface detectors were the same, you should get the same calibration to remove data for making that.
If the surface detectors are the same, apply the same.
Since you already have lots of fluorescence to fluorescence and surface detector co-measurements, do you need to do more?
Well, there are, I mean, you're saying, why don't we just stop doing fluorescence measurements? And, you know, things change with atmosphere and levels of light pollution and lots of things over time. So you really have to do this. The energy calibration really has to evolve over time. Kyle?
Actually, I think that answers my question now. I was going to just ask if the uncertainty was primarily in the shower or in the actual calibration of the detectors, the surface detection. It sounds like it's in the physics of the shower.
It's in understanding the models of what the lateral distribution of particles looks like, which at these energies we don't, you know, we're kind of in extrapolation land, not in interpolation land. Okay. I'd like to talk a little bit about my project, detecting cosmic rays by using radar technology. So I'm the spokesman for a group of 20-some physicists and electrical engineers from the University of Utah and some other institutions that are attempting to do this. Okay, the motivation is, well, we saw a map where we expand that telescope array by a factor of 4. You know, the truth is there's a lot of land in Utah into which we could expand, but we're getting to the point where these detectors get expensive. You know, the planned expansion of the TA surface detectors is, you know, going to be of order $10 million. You want to go a factor of 10 beyond that, you know, pretty soon you're talking real money. Are there any ways that we can do remote detection and cover the same area for less? And the radar detection idea is not new, dating back to the 1940s or so. People have looked for evidence of air showers in atmospheric radar. You know, people that study what's going on in the ionosphere with radar, and either not reported results or reported anomalies, but we're not able to, for sure, correlate those with cosmic rays because there was no cosmic ray detector present. A idea which comes to us from Helio Takai at Brookhaven is making use of bistatic radar. How that works is one has a transmitter, one has a set of receivers, and one has a set of shower detectors on the ground with which you can definitively say a cosmic ray shower passed through the atmosphere at a particular time. Okay? Then, you know, are you able to see the reflection of this incident wave? Okay? And although they had only very crude ability to reconstruct air showers, they seem to see coincidences in time, handful of coincidences in time in the MARIACHI project. Basically, what we're looking to do at Tara is take this idea, which made use of just local television stations and a crude set of high school-based surface scintillator detectors, ramp this up to the point where we're using a state-of-the-art cosmic ray detector and a transmitter that's in our control. Okay. So just a little bit about the physics. In any radar experiment, the question is, what is the cross section of what you're trying to see? And there are big uncertainties in that in the question of air showers. And different parts of the shower might contribute different amounts. This is a simulation of an air shower. Most of the shower particles, and therefore most of the ionization produced by the shower particles, are going to be out in what's called the underdense regime. They're fairly simple to understand the cross-section, but you suffer a potentially fatal effect, which is that the free electrons are going to collide with neutral nitrogen molecules in the atmosphere more than they're excited by the sounding radiation, and you're going to lose the signal. There's an overdense regime, which offers some hope because the the ionization density exceeds the critical density at which the plasma frequency is equal to the sounding frequency. Some questions here. The size of that might be fairly small, the order of a few centimeters, but should produce a stronger reflection, more like a macroscopic conductor. Now, so there's a lot of uncertainties in what the radar cross-section are. Independent of those, we can say some things about our signal is that it'll have a very distinct signature. And this is something that does not depend heavily on what the total cross-section is or how long the ionization lasts. These are all things that have large uncertainties. Okay, but because I have a shower front that's moving very close to the speed of light, I expect to see a very large Doppler-like frequency shift. Okay, this is a plot of frequency versus time here, and that is going to enable us to it's something very unique to look for in our receiver that's going to enable us to identify these signals. Notice that the size of this Doppler shift is of order several tens of megahertz in times of sort of 10, 20 microseconds. Okay. So this is the Tara research program. As I said, we want to study this radar technique, and this is really the ideal way to do it. There's a single TV transmitter in a radio quiet environment. We have a world-class cosmic ray detector facility, and we're able to make use of high sampling rate receivers, certainly higher rate than were available to Blackett level in the 1940s. We've sort of proceeded in two stages that I call Tara 1.5 and Tara 40. In one case, we used a relatively low power transmitter and a slow receiver, and just recently this summer are starting to look at data we collected with a higher power transmitter and a much higher sampling rate receiver. So the idea is a transmitter located either in cosmic ray center in the case of Tara 1.5 or just west of the town of Hinckley here in the case of Tara 40 is broadcasting sounding radiation across the surface detector array, okay, painting the sky above this region. Okay, an air shower comes and hits this region. Do we see or do we not see a radar echo from that air shower? This is just the Tara 1.5 equipment, a 54.1 megahertz at 8 kilowatts, effective radiated power. This is one of our receiving antennas out at Long Ridge. Nothing definitively that we can call a radar echo collected from the Tara 1.5 trigger scheme, although a handful of events where broadband noise was seen in time with cosmic ray air showers. Because the sampling rate of our receiver was fairly low, only about 12.5 megasamples per second, we really don't have the ability to reconstruct any chirp-like structure in that pulse. Okay, so as of this summer, we have a new 40 kilowatt transmitter that is online, and we're supplementing that with a array of Yagi antennas as opposed to a single Yagi antenna. We're now taking this 40 kilowatts, focusing it into a very narrow beam. The gain is close to a factor of 200, bringing our total effective radiated power to 8 megawatts. And thanks to those of you who came to our first light party on May 24th, helped us celebrate that. We're also upgrading the DAQ. This is a simulated event sampled at, well, let's see. This is an event a chirp that we broadcast, okay, at a signal to noise ratio of minus 10 dB SNR, and successfully triggered on with our new 250 megasample receiver with an onboard FPGA. So this is what a signal, at a very low noise rate should look like. Okay, so we're increasing our output power by a factor of 1,000. We're pushing our ability to detect signals, to trigger on signals, okay, down into the noise at a level of at a minus 10 dB signal to noise ratio. So optimizing hopefully our chances for success. So I've been going for 50 minutes. Steps in measuring the radar cross section. We'd like to understand that the shape of the radiated power, the shape of the main lobe, the radiated power. This is what is this lobe is what is being broadcast across the telescope array surface detector, and I'm torn whether to try to do this as a movie as I originally intended, or just to explain. Let me do it as a movie, as originally intended. Okay. So how much power is 8 megawatts ERP? And this movie is not in the interest of advancing anybody's knowledge about astrophysics, but this movie is about celebrating how cool it is that we make our living as physicists and some of the fun things we get to do. The transmitter is pointing to the southwest, which means that from Salt Lake City, it's basically pointing away from us. Nonetheless, if I go on the roof of this building and point a antenna to the southwest, okay, I can see evidence of our transmitter. Okay, so this spectrogram shows horizontal axis is frequency, vertical axis is time. Each of these dotted lines represents about 5 minutes. Okay. So in this case, we tuned to 400 hertz below the 54.1 megahertz signal. And although the transmitter is pointing away from us, it does have back lobes. It can scatter off of mountains and so on. And we are able to see the 54.1 megahertz carrier, okay, even though it's pointing away from us. What are some of the other features on this plot? Well, these kind of slow-moving arcs. Any ideas? Okay, these are airplanes, Doppler shifted signals from airplanes. Horizontal lines, okay, these are things that are short-lived on the time scale of 5 minutes, but very highly Doppler shifted. These are meteors, it turns out. In this case, these are going to be mostly micrometeors, things kind of the size of the grain of sand burning up in the atmosphere. But the coolest part of this plot, to me, is way over here at about 260. You see a very faint line. Do you see that? Okay, does anybody who I didn't already tell the answer, have any ideas what that is? Okay, this is the moon. This is the Doppler shifted reflection from the moon. Because the moon is setting, the Earth is rotating away from it, and you get a negative sign Doppler shift. Now, ham radio people reflect things off the moon regularly, but they do so at much higher frequencies. It's very hard to do this at 6 meters because of the rising galactic radio background. So that's just a sense of how big 8 megawatts ERP is.
How come there's no radio frequency interference? I mean, like you were saying, I would expect like cell phones or whatever to be
because we're tuned to 54.1 megahertz, which used to be channel 2 and now is nothing. So one of the reasons for doing Tara at this frequency is because we've got a wide open band in terms of, everything from channel 2 to FM radio is wide open to us. Okay. Also calibrating our receiver, understanding our noise floor in terms of the galactic background. We're able to do that quite well. Here's our carrier, but the noise floor that we see is very consistent with what is expected from the galactic background. Okay, and insert obligatory stay tuned joke here, and we'll tell you more as we learn things. Stay tuned to 54.1. Okay, so any serious objections to me talking for another 5 minutes about a fun, novel use for cosmic ray detectors? One thing I want to say before launching into this discussion is this quote is from our particle and nuclear axis physics funding officer at the NSF that he made in August. The U.S. budgetary climate for fundamental research is very challenging. For the most part, we are not aligned with the national priorities, climate, energy, et cetera. Okay? Potentially chilling words in the area of budget sequestration. Okay, is there anything that we can do with our detector to maybe put us, make us more interesting to them in terms of national priorities? It turns out that it's been known for a decade or so that lightning emits high energy particles. This was first seen in rocket-triggered lightning. So you put a rocket on top of a tower, you shoot it up in the air during a lightning storm, trailing a wire. Okay, lightning travels down that wire, and you can have some gamma ray detectors on the ground and observe high energy radiation that comes from lightning. This was a decade ago. Since then, this has been seen in natural lightning as well. But the precise mechanism for producing these high energy particles within lightning is unknown. So wouldn't it be nice if there were a type of detector that could detect high energy particles and even reconstruct the directions that they're coming from? Okay. And I'm not allowed to tell you this, but there's some evidence within the telescope array data that we have just the ability to do just that. Publication forthcoming. Another question: do cosmic rays seed lightning? If one looks at the typical electric fields that are present in clouds during electric storms, one finds typically measurements that max out at about 3 kilovolts per centimeter. Okay, now as every person who has taken physics 2220 knows, the breakdown potential of air is about 30,000 volts per centimeter. Okay, so about 10 times that. So why is air breaking down during electric storms and producing these sparks? Okay, is something happening to seed these events? Okay, and a paper from Dwyer, he's the same fellow in Florida who did the rocket-triggered lightning, suggests that runaway relativistic electrons that come from air showers above about 10 to the 16th electron volts might be the cause of that. So two kind of interesting questions that we can address in TA. Okay, one, can we understand how lightning produces high energy particles? Two, can we answer this really tantalizing question? Okay, do cosmic rays seed lightning? And this is the one that really excites me. I mean, as long as there have been people on Earth where does lightning come from? If we had a chance to answer that question, you know, if there's something more exciting than that, I don't know what it is. This is just something we've been doing for the past several months now. We installed a lightning mapping array along with some folks from the Langmuir Institute at New Mexico Tech to reconstruct lightning that happens above the telescope array surface detectors. And here's a website that you can look for hourly updates. I'll show a slide from that in a minute. And we're submitting a full proposal to the National Science Foundation in October. This is the results of one of the first days. You know, fortunately, we're deploying this during the lightning storm season. And so here, this is a map of Utah. The red here is Millard County, and the green squares represent the lightning mapping array detectors. And each dot here represents a lightning strike that was observed. So potentially we've already got some interesting data to look at. And okay, moving number 2. I promise this is it. Okay, so this is an example of the output that this lightning mapping array is capable of producing. How this works is, you know, you think of lightning as being a smooth discharge of current from the cloud to the ground. In fact, if you looked at it at a sort of microsecond or tens of microsecond time scale, what you would see in lightning is a series of little breakdowns. Bzz, 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 bzz. Each of those little bzz produces some current that you can pick up in a detector. If you've got 4 or more of those detectors, or excuse me, 5 or more of those detectors, you can get the X, Y, Z, and T of that little bit of current. And you know, what this video shows is the evolution of time of an actual lightning strike. This one was in New Mexico, not a telescope array yet. So you see the color represents time, and you know, so the dream is, okay, on top of a display like this in 3 dimensions, have an air shower reconstructed by the telescope array surface detector, superimposed. I think this is a very exciting prospect. And I'm almost done, I swear. Okay. So to recap, we are deploying 3D lightning maps. Very compelling physics. We know that we are going to contribute to the answering the question, how do high energy particles get produced in lightning? There is a speculative, but I think very important question that we can answer: do cosmic rays seed lightning strikes? And another important thing is it's a broader impact bonanza in NSF terms. What do I mean by that? We told Jim Whitmore that we were planning on submitting this proposal, and I heard back from him a few weeks later that he wanted materials from us to talk about the lightning mapping array, the telescope array lightning mapping array, and a highlight talk about NSF projects. Okay. So just telling him that we intend to submit the proposal excited him enough that he wants to start bragging about us already. So we regard that as a good sign. Something else we can do with cosmic ray detectors. And I'm over time, so you can look at my conclusion slide and ask me questions. Thank you.
Chad's only over by 3 minutes according to my watch, so we have time for a few questions. Carlton?
So is there any way you could measure the radar ion channel cross-section in the laboratory? I had to make
selective choices in what I presented today. One of the facilities that we have at Telescope Array is the electron light source, which is a politically correct term for a 40 MeV electron gun that shoots a beam of electrons up in the air that we can calibrate our fluorescence detectors with. So that might be our best bet at doing that. We've looked at it. There are some challenges. Other sources of noise that are emitted when the ELS is firing. But yes, we are pursuing just that, seeing if with a known source of atmospheric ionization we can see some evidence for this type of radar reflection.
Is the expansion of the TA project, is that to just have a larger area for showers to fall into, a larger effective area, or is there a larger baseline associated with that?
What do you mean by baseline exactly?
Like, does having the larger area just give you a larger space for things to fall into,
The number of cosmic rays we detect per unit time depends on the area.
Okay.
So, yeah, basically that's it. I mentioned that the spacing was different. The spacing is larger for the TA times 4 array than for the core array. Basically, we're making a trade-off between efficiency for detecting lower energy showers and having a higher aperture for high energy showers. But basic goal is increase the area at the highest energies in which we're reflecting more cosmic rays to hopefully nail down the question of these marginal hotspots that we may or may not be seeing.
Ollie? So just to understand a broader picture, so there is another big experiment running, which is IceCube, right? Detection experiment. Is there any interplay? I mean, is there any potential for kind of them getting some of the data you're interested in, or you looking at the data? I mean, is there, because it's a huge scale thing.
Yeah, so IceCube, of course, is focused on neutrinos, neutral particles. So it's in a sense it's a complementary to the types of measurements that we're doing. Different messengers that we're studying. The neutrinos, because they're undeflected, because they're produced in the GZK process itself, can give us important clues, mapping out the sky, finding what are the sources of particles potentially at this energy. So I would characterize that what is being done at IceCube is kind of complementary measurements to what we're trying to do with charged particles.
Can I add something? IceCube is centered on lower energies, but there's another experiment called the Ascarian Radio Array, ARA, which has been proposed, which would be much larger than IceCube, and they should see, of the GZK neutrinos, they should see 10 per year or something. About 10% of that experiment has been deployed, and they're now taking test data.
And another connection, I might make. It's of course possible in principle to detect neutrinos in atmospheric interactions, as well as in large blocks of ice at the South Pole. Again, the question there is one of aperture. Okay, so increasing the aperture of detectors is going to increase our chances of detecting these neutrino events. Really, that's a big motivator for the radar project to increase apertures to areas the size of the state of Utah and larger, so we have some hope of doing that. It's the dream anyway.
Do you know if there'd be any way, maybe thought about this, or I don't know, there are these next generation radio telescope arrays like LOFAR and SKA, whether it would be possible to design some sort of co-observing scenario, like maybe you can build a giant ring of transmitters around them, and then they can do real-time beamforming.
So those detectors are all using radio or, I mean, microwaves in some cases that are generated by the showers themselves, okay, as opposed to radar where we're using some sounding radiation. So, yeah, so it's not clear. I mean, in fact, it might be we might just be adding background if we start dumping our carrier signal into there. So a difference between the radio detectors like LOFAR and TARA, you have to have a radio detector on the ground, the same way you have to have a surface detector on the ground to detect the LOFAR radio emissions. Okay, so in terms of going to a remote sensing technique, LOFAR doesn't gain you anything. You're looking at the air showers in another channel, okay, but you still have to cover the ground with radio detectors, which is a little different from the TARA philosophy that you cover.
Yeah, so I know you have to put in carrier transmitters as well. I'm just wondering whether that's something that they could effectively filter out in different bands or whether that's, like you say, a real source of background that could be considered.
Yeah, haven't focused on that yet. Right now the big thing for us is, can we see the echoes? Do they follow the models we expect? The frequency versus time development, and is the cross section big enough that these remote detection dreams that I'm talking about is realistic?
Andre?
So, maybe I don't remember this correctly, but I think several years ago there was a paper from joint collaboration claiming that high energy cosmic rays actually coming from centers of galactics, and then apparently it was refuted by your group, your computer, and now you are saying there is some correlation between mass and cosmic rays coming. So, can you comment on this? Are we talking about the same thing, or maybe I just this picture, right?
So the original OJ result, which was published in Science in 2007, 2008-ish, that result was refuted, I think, most strongly by OJ's own data. Okay, so looking only at the data that was collected after that publication, the significance of correlation went to nothing. High-res looked in the north as well, with lower statistics, did not see a correlation. So the telescope array data is now getting to the point where the statistics we can start to make sort of statistically significant statements. I'm trying to back up to my plot. Okay, about these events. By eye, it looks like there's some clumpiness there. If one interprets things in terms of the large-scale structure, it seems like there's some low significance, couple percent chance probability effect. Do the distribution of catalog objects that Auger used follow this large-scale structure? Yeah. There's going to be correlations between where active galactic nuclei and what are the large-scale what's the overall large-scale structure? Is this the same signal? Is it a related signal? Is it apophenia? Am I answering? Okay, so
the question wasn't well defined.
okay. I'm just kind of yeah, so the original claim of Auger that there were, you know, at the 3 standard deviation level, correlations with active galactic nuclei in a particular catalog has, that effect is going away. Okay? This is a fairly new result from, so we've just gotten to the point that we can do with TA. We might expect there to be some correlation between this structure and the types of events in the Auger catalog, or in the Verone study catalog that Auger saw correlations with. So are we still looking at AGNs? Are we looking at other structures that follow the large scale structure? Is this effect real at all?
How do we know that there are no electric fields in the atmosphere above 3 kilovolts per centimeter?
Lightning detecting experts can fly balloons in electric storms and also do measurements on the ground and use those to.
There's never been basically a significant or hardly any increase.
Well, I'm not a lightning expert, so I can't say that there's never been.
Yeah,
But typically fields are about an order of magnitude lower than what you would expect.
One last question.
So how does the lightning detector, you have all these little arcs, how, what is the hardware that is getting all these little arcs that is, I assume,
The hardware is a antenna. Now this is kind of amusing. Tara, we're using channel 2. Guess which channel the lightning mapping array uses?
3. Channel 3.
Lightning mapping array uses channel 3. Which happens to be a place where there's a lot of radio emissions by lightning. So this is just a dipole antenna. These three prongs here are actually a ground plane, just to increase your antenna gain a little bit. But basically, this is a channel 3 receiver.
Channel 3 is just the length.
Channel 3 is the bandwidth.
Yeah, but so the length is fixed.
So the length is half the wavelength or so. I guess this must be a quarter wavelength. What was I going to say? So a channel 3 receiver, but you sample it at 10 megasamples per second, basically. Find the largest amplitude pulse in a 10 microsecond window. So for every little current blip, right, there's an X, Y, Z, and T. So if you have 4 or if you have 5 measurements or more, you over-constrain the possible locations where that blip is coming from in 3 dimensions, and then you do that 10,000 times or so, and you've got a lightning strike.
Can you tell the direction of that blip? That blip presumably is also radiating in a dipole pattern section.
So with this detector, no. But you can see how in the movie you saw how it evolved with time, right? Each blip you see one after the other. That's how you get which way the lightning is moving. You're going from the cloud to cloud, cloud to ground, positive polarity, negative polarity.
I think that John has raised all kinds of physics questions and scientific questions here, which we could just keep discussing for a long time. But it's now 12:18, so let's thank John again